Now, so we know what is the effect of the height and depth, okay, on acceleration due to gravity of Earth. Okay, so we know now what is the acceleration due to gravity at height h and what is the acceleration due to gravity at depth d below the Earth's surface. Okay, now we'll find out the effect of rotation of Earth on the acceleration due to gravity. Okay, so we know that Earth rotates about this axis which passes through its north and south poles. Okay, so because of rotation of Earth, what will happen? Every point on Earth will perform circular motion, right? Every point on Earth will perform circular motion. So let us suppose this is the equatorial plane. Okay, so if we consider a particle which is here, okay, this is some location, let's call it point P. So our particle is at point P. So this particle, it will revolve in a circle like this, right? It will revolve, it will perform circular motion in this circle. Okay, so let's suppose radius of this circle is r. Okay, let me use black color only. So radius of this circle, suppose small r. So this is the center of Earth, let's call it O. So this much distance, okay, this much distance is capital R. Okay, this much distance is radius of the Earth, right? And this is the position vector of this particle with respect to center of the Earth, we can say. Okay, so this position vector makes some angle with this plane, the equatorial plane. So this angle is known as latitude. Okay, this angle is known as the latitude, right? So I'm sorry, this angle, it is known as latitude, denoted by phi. Okay, so now let's suppose this point is O dash. So O dash is the center of revolution of this particle, right? This particle will revolve in this circle. Its center is O dash. So if you think about this rotation, so let's suppose omega is the angular velocity of Earth. Okay, so same will be the angular velocity for this particle also, for this circular motion, right? And we know that circular motion is an accelerated motion. Okay, circular motion is an accelerated motion. So the object which is here, anybody, let's suppose any object or any person who is here, he will be in accelerated frame of reference. Okay, so in accelerated frame of reference, we make use of pseudo force. We make use of pseudo force, right? So for this particle, there is an outward force acting on it, okay, which will cause the outward acceleration. Okay, the particle or the person who is there, you will feel that there is some outward force acting on it, right, which we call pseudo force. And how much will be its magnitude? Its magnitude is equal to mr omega square, right? So there is pseudo force, let's call it fp, is the pseudo force or this person who is revolving, okay, due to the rotation of Earth. Okay, so he feels that pseudo force which is equal to mr omega square, right? So now see the he is attracted towards the center of Earth and there is this pseudo force acting on it, okay, acting on him or her. Okay, so now there will be some component of the pseudo force which will act in this direction, right? This component of pseudo force will act in this direction. So now for this person, he will feel like for this direction there are two forces acting on him. okay, him or her. So one is the force due to gravity, which is acting towards the center of Earth, and one is this component of the pseudo force. Okay, so this component is Fp cos phi. We can say this angle would be phi. So it is Fp cos phi, right? So now how much would be net force? Net force, okay, on particle at P, particle or person at P towards the center, towards center of Earth. So let's call it F net. It will be equal to the force due to gravity, minus the pseudo force Fp. Okay, so which is equal to, we can write it as mg. So where g is the acceleration due to gravity, normal value of acceleration due to gravity, minus the pseudo force is mr omega square, right? And for this person, then the net force towards the center of Earth will be equal to what? The mass of the person, okay, or mass of particle, whatever, mass of object, multiplied by effective value of the acceleration due to gravity at that point. Okay, so it is mass of the person multiplied by effective value at that latitude, we can say. Okay, it's not only for this person, every particle or everything at that latitude will feel the same value of acceleration due to gravity. Okay, so it is m times g phi is equal to m multiplied by g minus r omega square, right? R omega square, sorry, the component in this direction will be what? The this force is mr omega square. So component in this direction will be mr omega square multiplied by cos phi. Okay, the cos component, right? So it is mr omega square multiplied by cos of phi. Okay, so it is r omega square multiplied by cos of phi, right? And then m can be cancelled out on both sides. Okay, so g phi is equal to g minus r omega square cos of phi, and this small r, okay, if we relate small r and capital R, what will be the relation? So see, this angle is also phi. Okay, it's vertically opposite angle for this one. It is also phi. So cos of phi is this small r divided by capital R. Okay, so we can say cos of phi equals to small r upon capital R, and therefore small r is equal to r times cos of phi. Okay, so this is equal to g minus r cos phi multiplied by omega square cos phi, or you can say it is g minus r omega square cos square phi. So this is the effective value, I'm sorry, this is the effective value of acceleration due to gravity at the latitude phi. Now we'll see two special cases. So one is phi equals to 0, that means object is at equator. Okay, so at equator phi is equal to 0, and at poles phi equals to 90 degrees. So we know that cos of 90 is 0. Okay, so cos 90 is 0, right? So therefore this term will be 0 at the poles. So acceleration due to gravity at poles is just equal to g, normal value of g, and it has no effect due to the rotation of Earth. Okay, there is no effect of rotation of Earth on acceleration due to gravity on poles, right? But at some other latitude phi there will be some effect, and the effect is maximum at the equator, because at equator phi is equal to 0. So we can see that cos square phi, cos of phi will be equal to 1, cos square phi is equal to 1, and therefore acceleration due to gravity at poles is just g minus r omega square. Okay, it is g minus r omega square. So is this thing clear? Yes, no? Next, let us talk about the gravitational potential energy. Okay. So let's talk about gravitational potential energy. I'm sorry. Okay. So what is the gravitational potential energy? Okay. So let's suppose this is Earth's surface, right? So here, let's suppose there is some object. Okay, this person is here. He throws some ball in air, and that ball reaches to some height. Let's call it h. So we say that its potential energy at that height is how much? It is equal to mgh, right? It's equal to what? Mgh. Okay. So potential energy at height h is equal to mgh. So what is that? It is the work done against the gravitational force. Okay, it's the work done against the gravity. I'm sorry. So it is the work done against the gravitational force. Here, in this example, when this man throws the ball vertically upwards, okay, the gravitational potential energy of this ball increases, right? So as the ball goes away from Earth's surface, its gravitational potential energy increases. So the gravitational potential energy at height h is equal to what? Mgh. When we throw the ball upwards, okay, when it goes till height h, its gravitational potential energy is equal to mgh. So that means when h is equal to 0, when h is equal to 0, what will be the value of potential energy? It is equal to 0. Okay, so we can use this. We can use this formula for the gravitational potential energy for small heights when the height is very small compared to the radius of Earth. Okay, but when the height is comparable to radius of Earth, we cannot use this formula. Okay, then we cannot use this formula. Okay, so in this example, what do we consider? The potential energy on Earth's surface is 0. So as height changes, the mass will gain some potential energy, and that is equal to what? Mgh. Okay. So actually what we can measure is only the change in potential energy and not the actual potential energy. Okay. So this is just convention that we take the potential energy on Earth's surface equal to 0. This is just a convention. So let's suppose this is Earth, and there is some object which is okay, there is some object which is initially at distance r1. There is some object which is initially at distance r1 from the Earth's surface. Okay, and you move that object from r1 to r2. You move that object from r1 to r2. Right. So now, how much will be the change in potential energy of the object? So there is object of mass m which is moved from distance r1 from the center of Earth to distance r2 from the center of Earth. Okay. So now when it is at some position r, so how much would be the gravitational force acting on it? The gravitational force, okay, F is equal to what? G times m into m upon r square. This is what we know. Okay. So gravitational force acting on this mass is equal to G times capital M, mass of Earth, multiplied by small m, mass of this object, upon r square when it is at distance r away from center of Earth. Now when we move it from this distance r to r plus dr. That means when we displace it by distance dr, the work done would be equal to what? This force multiplied by displacement, right? So work done against against gravity, gravity of whom? Gravity of Earth, to move the object, to displace this object of mass m from r to r plus dr. What is that work? Work is dw, and it is just equal to what? F dot dr, or we can say is equal to g times capital M into small m upon r square into dr. Okay, so because work is done against the gravitational force of Earth, okay, this will be positive work done by some external agency, right? So now this work will change the potential energy of the object. Okay, so now we are moving it from r1 to r2. Okay, so work done to move it, to displace it, from r1 to r2 will be equal to, what will be the work done? So work done will be what? Integral of this f dot dr from r1 to r2. Okay, so it is 1 upon not 1 upon gmm divided by g times m into m upon r square dr, integral of this from r1 to r2, sum r1 to r2. Okay, so this is equal to, so g times m into m is a constant, we can take it outside of the integral. The g times m into m we take outside, so it is just integral of, you can say, 1 upon r square or r raised to minus 2 dr from some r1 to r2. Okay, so this is equal to g times mm multiplied by, so what would be this integral? So we know integral of r raised to n dx is just r raised to n plus 1 divided by n plus 1, whatever are the limits. Okay, so here n is equal to minus 2, so this integral will be what? It is r raised to minus 2 plus 1, that's minus 1 divided by minus 1. Okay, r raised to minus 1 upon minus 1, or we can write it as, so this is from r1 to r, or we can write it as 1 upon r raised to 1, okay, or 1 upon r multiplied by this minus 1, so that is minus of 1 upon r, so it is g times m into m multiplied by minus of 1 upon r from r1 to r2. Okay, right? So we'll substitute the values of r1 and r2, but I will take that minus sign common or minus sign outside. It is minus of g times mm multiplied by 1 upon r2 minus 1 upon r1. And we know that this is the work done against the gravitational force. So this gets stored as what? This gets stored as the potential energy. Okay, so this is the change in potential energy of that object when it moves from r1 to r2. So it is equal to final potential energy U at position r2 minus initial potential energy at position r1, right? So okay, so this is change in potential energy. So is there any question till this point? So let's consider this case where r1 is infinity and r2 is equal to r. That means initially the object is at infinity and you are bringing it from infinity to r. Okay, you are bringing it from infinity to r. Okay, so object is at infinity, it will have some potential energy. then you are bringing the object from infinity and keeping it at distance r away from the center of earth, right? So we have u of r minus u at infinity is equal to minus g times m into m multiplied by r2 is r minus initial position is infinity. Okay, so this 1 by infinity means 1 by 1 divided by very large distance will give us 0. Okay, so when distance tends to infinity, 1 upon distance tends to 0. So the second term will be equal to 0. Okay, will go to 0. So we have g times mm divided by r is u at position r. So potential energy of the object when it is at distance r away from the center of earth minus potential energy at infinity. Okay, so what we have is the difference between potential energy at distance r and at distance infinity. Okay, so difference between potential energy when the object is at distance r from the center of earth to when it is at distance infinity from the center of earth. This is what we have. Okay, and now we use a convention. So we make use of this convention. So this is purely a convention. Okay, but it is convention which helps, right? So potential energy at infinity, we consider it to be 0. So this is a simplification. It doesn't really matter. It can be any constant. Okay, we can have potential energy at infinity equal to anything. It doesn't matter. It will just add up in the formula for potential energy everywhere, right? So you write potential energy at infinity equals to 0. Okay, so then what do we get? Potential energy at distance r away from the center of earth is just gmm divided by r. So potential energy of an object at distance r from the center of earth is gmm upon r. Okay, and this r can be written as what? Capital R plus h. So this r can be written as, small r can be written as capital R plus h. So what do we get? We get potential energy at distance r is equal to minus of g times m into m upon r plus h. Okay, then in gravitation there is a useful trick. Okay, so we know that gh is equal to what? G times m upon r plus h square. Okay, we learnt about this yesterday, right? So we can write g times m is equal to gh into r plus h square, or when h is equal to 0, we can write it is just g multiplied by r square. So we can substitute that here. So what do we get? We get potential energy at distance r away from earth, which can be written like this: potential energy at r plus h, or at height h, okay, is equal to minus of, this is gh multiplied by r plus h square. Okay, so in place of gm I have written gh multiplied by r plus h square, multiplied by, you have this mass m divided by r plus h. So this r plus h will get cancelled out with this 2. Okay, I mean square divided by r plus h. So we will give you r plus h only. So it is equal to minus of gh multiplied by r plus h into mass m. So is it clear? Yes, no? There is a question. Okay, so this is gravitational potential energy. Then we define the gravitational potential. Okay, gravitational potential due to Earth. So gravitational potential at distance r is equal to work done per unit mass to bring that mass from infinity to r. Okay, so gravitational potential is denoted by letter V. So V is equal to what? Work done to bring a mass m from infinity to r divided by, sorry, divided by that mass. Okay, so it is work done per unit mass to bring that mass from infinity to distance r. Okay, so we can write V, or we can call it V at r. Okay, so it is equal to, now if we divide by mass, what do we get? So we know this is equal to what? Work done is gmm divided by r. So if we divide this by mass, so this mass and mass gets cancelled. So what do we get? We get minus of g times m upon r. Minus of g times m upon r. Or similarly, we can write this is equal to, okay, again we can make use of gm equals to gh multiplied by r plus h square, or r square, small r square. Okay, small r is equal to r plus h. So if we substitute that, what do we get? We get minus of what? Gh multiplied by r square upon r. Okay, so that is gh into r only, right? So now we don't have to remember all of these formulae. We just have to remember this trick. Okay, so for gravitational potential energy, we'll just remember this one and only one formula. Okay, wherever required, we can convert it to this formula. Okay, we can convert it to this formula, right? Then for gravitational potential also, we'll remember only this formula, and wherever required, we can convert it to this formula using this trick, this substitution. Let's see one more thing. Okay, and that is the escape speed. Okay, so what is escape speed? So it is the speed with which object must be thrown such that it escapes the Earth's gravitational bound. Okay, it is the speed with which object must be thrown such that it escapes out of Earth's gravitational influence. It goes to infinity, right? So how much should be that speed? So now we know what is the potential energy of object at distance r. So it is u at r is equal to what? Minus of g times m into m divided by r. Okay, so this is the potential energy of the object. Then we give some kinetic energy to it. Okay, so kinetic energy that we give would be equal to what? Half of m into v square. Okay, but by giving this kinetic energy, okay, by throwing that object from that height, we are expecting it to go beyond infinity. Beyond infinity meaning not beyond infinity, till infinity. Okay, so what would be its final kinetic energy? Okay, so I can say, okay, so we are giving some speed which we are calling what? The escape speed, V suffix e, right? So its kinetic energy is equal to half of mv square. Okay, so let's suppose this kinetic energy sufficient to make that object escape out of what? Earth's gravitational influence. Then we can write u at position r plus k at position r is equal to u at infinity plus k at infinity, right? This is just law of conservation of energy. Then what is u at r? The gmm divided by r. What is k at r? Half of m into v square. And potential energy at infinity is equal to what? We consider it to be 0. Okay, and from there only we get this formula. Plus kinetic energy at infinity is half of m into v infinity square. Okay, so now v infinity can be at least 0. Okay, v infinity will be 0 or greater than 0, right? So for minimum value of this velocity or the speed, the v infinity will be equal to what? It will be equal to 0. So let's substitute v infinity equals to 0. That means the object just goes to infinity. Okay, it escapes the Earth's gravitational influence. It goes to infinity and stops there. Okay, there it doesn't have any velocity. Okay, so v infinity will consider it to be 0. Find out minimum speed which must be given to the object such that it goes to infinity. Okay, so let's put v infinity, sorry, v infinity also equal to 0. So what do we get? We get half of m into v square is equal to g times capital M into small m divided by r, and this m and m gets cancelled. So we can take the 2 on the other side. So what do we get? We get v square is equal to 2 times of g times m upon r. That means v is equal to square root of 2 times gm divided by r. Okay, so if object is at distance r from the center of earth, the minimum speed which must be given to the object such that it escapes earth's gravitational influence is square root of 2 gm upon r. Okay, and that r can be always written in terms of the radius of earth and the height. Okay, so it is square root of 2 times gm divided by r plus h, right? And again, what we can do is we can write gm is equal to gh multiplied by r square. If we substitute that here, what do we get? Escape velocity is equal to square root of 2 times of 2 times of gh into r, or I can say it is equal to square root of 2 times of gh multiplied by r plus h, right? And on earth's surface, on earth's surface we can say escape velocity is equal to square root of 2 times gm divided by r only, because h will be equal to 0. Okay, or it is equal to square root of another formula. So in place of gh we'll have g, acceleration due to gravity on earth. So the square root of 2 times g multiplied by r. Okay, and its value, so if we substitute g equals to 9.8 meters per second square and radius of earth is 6400 kilometers, then it comes out to be 11.2 kilometers per second on earth's surface. Okay, so the escape velocity, the velocity with which must some object must be thrown, or some person which you dislike. Okay, the velocity with which that person must be thrown such that he will never come back. It is 11.2 kilometers per second. So got it? Yes, no? So now let us see some problems based upon this. R is radius of Earth, omega is its angular velocity, and Gp is the value of G at poles. The effective value of G at the latitude lambda equals to 60 degrees is. So what is the effective value? G at latitude lambda. Okay, so latitude we denoted by pi, they are denoting it by lambda. So it is equal to what? G minus R omega square cos square phi, or they are calling it lambda, so let's call it lambda. Okay, so it is G at poles is equal to G, so we can write this as G at poles minus R omega square multiplied by cos of 60 degrees square. And how much is cos 60? 1 by 2, right? So it is 1 by 2 square, 1 by 4. Okay, so it is Gp minus what? 1 by 4 R omega square. Option A. Next question. If the rotational speed of Earth is increased, then the weight of a body at the equator, what will happen? It will increase, decrease, becomes double, does not change. Tell me. G at equator is equal to what? G minus R omega square. If rotational speed is increased, what will happen to the weight? So we know that weight is equal to what? Weight of an object is gravitational force acting on the object, right? So if omega increases, then weight decreases. Good. Okay, this was simple. Next question. The acceleration due to gravity on Earth's surface at the poles is g, and angular velocity of the Earth about the axis passing through the pole is omega. An object is weighted at the equator and at height h above the poles by using spring balance. If the weights are found to be same, then h is. So, and they are giving h is very small compared to r. That means we can use gh is equal to which formula? G multiplied by 1 minus twice h upon r. And they are calling this is equal to what? G at equator. Okay, the weight of object is same means acceleration due to gravity is same. And what is G at equator? So G at equator, okay, I will write this as G minus G multiplied by twice h upon r is equal to G at equator is G minus r omega square. We know this. Okay, so this G and G will get cancelled out, right? Yeah, G and G will get cancelled out. So we have h equals to what? Okay, we have 2 times h multiplied by g by r is equal to r omega square. So if we take this 2g and r on other side, we get h equals to r square omega square divided by 2g. Okay, so option A is the answer. The work done, to raise a mass m from the surface of Earth to height h, which is equal to radius of Earth is. Okay, so now we cannot use change in or work done against the gravity equals to mgh. Okay, we have to use the other formula, right? So work done is equal to what? Potential energy at height h minus potential energy, okay, at r, right? So potential energy at height h, we know it is minus of g times m into m divided by r plus h. minus potential energy on Earth's surface is minus of g times m multiplied by m divided by r. Okay, and then h is equal to how much? Radius of Earth. Okay, so in place of h, I will put r. Okay, so this is minus of, we can say, half of gmm upon r, because in denominator we have 2r, plus 1 gmm upon r. Okay, or you can say 1 minus half gmm upon r, so it is half gmm upon r. Okay, so which is the answer? And you can substitute gm equals to gr square whenever you want. Okay, so let's substitute that. So when you substitute that, you get what? It is equal to half of mgr, right? Option D. Next question. So at what height from the surface of Earth the gravitational potential and the value of g are minus 5.4 into 10 raised to 7 joules per kg and 6 meters per second squared respectively? Take the radius of Earth equals to 6400 kilometers. Okay, so they are asking at what height the gravitational potential, which is v is equal to this thing, okay, this one, and g is this much. So we know v is equal to minus of gm upon r plus h, right? Okay, so they have given it in terms of acceleration due to gravity. That means we have to use other formula. So gm equals to gh into r plus h square. If we substitute that, we get it is minus of gh multiplied by r plus h. Okay, and now we just have to substitute the values. Okay, so this is minus 5.4 multiplied by 10 raised to 7. It's equal to minus of gh is 6 multiplied by r plus h. Okay, so this is 54 multiplied by 10 raised to 7 divided by 6. So how much is that? 9. 9 times 10 raised to 6. Okay, so r plus h equals to 9 multiplied by 10 raised to 6. How much is r? It is 6400 kilometers. Okay, so r is 6400 kilometers, or you can say 6.4 multiplied by 10 raised to 3 kilometers. Okay, and if you want to convert it into meters, so 1 kilometer is 10 raised to 3 meters. So we can write this in meters, so it will be 6.4 multiplied by 10 raised to 6 meters. Okay, so then we substitute that here and take it on other side. Okay, so that it gets subtracted from this number. So we get h equals to 9 multiplied by 10 raised to 6 minus 6.4 multiplied by 10 raised to 6. Okay, so how much is that? It will be 2.6 multiplied by 10 raised to 6 meters, or we can say 2600 kilometers, right? Oh, you said option C? Good. All right, next question. An infinite number of bodies, each of mass 2 kg, are situated on x-axis at distances 1 meter, 2 meter, 4 meter, 8 meter respectively from origin. So there are infinite bodies and all of them have mass 2 kgs, 2 kg. Okay, at distance 1 meter, 2 meter, 4 meter. There is nothing at 3 meter, 4 meter, 8 meters respectively. So m, so on and so forth. Then the resulting gravitational potential due to this system at the origin will be, okay, the resulting gravitational potential due to this system at the origin will be. So this is a good question. So what is gravitational potential? Minus of G multiplied by M upon R. Okay. So if there are n number of bodies, for them the gravitational potential will be equal to what? Net gravitational potential will be equal to sum of gravitational potential due to all of those bodies. Okay. So it is square root, sorry, minus of Gm upon R1. So R1 is 1, right? Okay. R1 is 1. Then we can take minus sign common actually and multiplied by Gm upon R2. R2 is 2 plus Gm divided by R3. R3 is 4 plus Gm upon R4. R4 is 8. Okay. So we can see what's happening here. This is a series. What kind of series? It is a geometric series. Okay. What is the ratio? So if this is if this is first term in the series, so if you multiply first term by half, you will get second term. Okay. Then if you multiply that by half, you will get third term. So on and so forth. Right? So this is a geometric series, and this will go till infinity. There are infinite such bodies. Okay. So what is sum of a geometrical series? Geometric series? It is A divided by 1 minus R. A is the first term, right? And R is the ratio. Okay. So it is equal to minus of Gm, we can say. How much is M? M is 2 kg. Minus of G times M, let me write, multiplied by 1 upon 1 minus R. Okay. But this R is ratio, not distance. Okay. So minus Gm or G times 2 multiplied by 1 upon 1 minus half. Okay. So how much is that? This will be half. Take it into the numerator, it will become 2. 2 times 2 will be 4. Okay, so minus 4g is the answer. Option B. Right? Next question. Body of mass m is taken from Earth's surface to a height equal to twice the radius of the Earth. The change in potential energy of the body will be. Okay. So again now it's the similar question to what we have seen, right? So how much is change in potential energy? So work done is equal to final potential energy minus initial potential energy. So minus of Gmm divided by R plus H minus of minus Gmm divided by R, because body is moved from Earth's surface to height h. So this is change in potential energy. Okay. So it is equal to minus of G times M multiplied by M divided by R plus how much is height? Height is twice the radius R. Okay. So R plus 2R will give us 3R plus we have Gmm divided by R. Okay. So 1 minus 1 by 3 we can say multiplied by Gmm upon R. So it is 2 by 3. Right. So it is 2 by 3 Gmm upon R. And then we can substitute Gm equals to Gr square. So then this will be equal to 2 by 3, okay, multiplied by mgr, right? Yeah. Let's discuss next question. Particle of mass m situated at center of a spherical shell of same mass and radius a. The magnitude of gravitational potential at point situated at a by 2 distance from the center will be. So you have a shell. So due to this shell, there will be some gravitational potential. Okay. So how much would be gravitational potential due to shell? See, now here comes this concept that, okay, what is gravitational potential? It is work done per unit mass, right? It is work done per unit mass. Okay. So, okay, how much would be gravitational potential at this distance? There is a mass m situated at the center of spherical shell, and mass of the shell is also m. Okay. So now, see, the gravitational potential inside the spherical shell is constant. Okay. Gravitational potential inside the spherical shell is constant. Okay. How, why is that? Okay. What's the reason? So see, the field, gravitational field inside the shell is equal to 0. We had discussed that. Okay. The gravitational, see, it doesn't exert any gravitational force. Okay. Shell doesn't exert any gravitational force on any mass which is kept inside it. Okay. So gravitational force is equal to 0. So if force is 0, okay, force is 0, what will be the work done to move a mass inside the shell? It will be 0. Yes, no. Okay. And that means how much would be difference between two points, sorry, potential energy of a mass at 2 points inside a shell. Since work done is 0, okay, the difference in potential energy is 0. Yes, no. Okay. So difference in potential energy is 0. Okay. And that means potential will be same. Okay. So let me explain this concept nicely once again if there is some confusion. So the question is, a particle of mass m is situated at the center of spherical shell, okay, of the same mass and radius a. Magnitude of gravitational potential at a point situated at a by 2 distance from the center will be. Okay, so we have this shell and its mass is m. There is another mass. There is another mass at the center of the shell, and that mass is also m. Okay, and now question is the magnitude of gravitational potential at a point situated at a by 2 distance from the shell, from the center. So this much distance is a. You want to find the potential here, okay, at distance a by 2, right? At distance a by 2. Okay, so this much distance is a by 2. Now see, if I take a spherical shell, okay, then its mass can be anything. It doesn't matter. Now let's suppose there is a mass, small mass m inside that shell. So we know that the shell exerts no force on that mass, no gravitational force on that mass. Okay, so gravitational force on this mass is equal to 0, right? So therefore, now if I move this mass from, let's say, this position, let's call it A, to some other position B, inside the shell. Since if mass is at position A or position B, there is no force acting on it due to the shell. Okay. So since there is no force, work done will be equal to 0. Okay. So work done to move it from A to B. A to B is equal to change in potential energy of that mass. Okay. So that is final potential energy minus the initial potential energy. And since work done is equal to 0, you can say potential energy at B is okay minus potential energy at A is equal to 0, or potential energy at B is equal to potential energy at A, right? Then see, now how do we define potential? Potential is work done per unit mass. Potential is work done per unit mass, right? So now, okay, so see, since potential energy at U is equal to potential energy at B, and it will be equal to potential energy on the surface of the shell. Okay, it will be equal to potential energy on surface of shell. You can consider this mass just over here. Okay, so therefore the potential inside shell due to shell is constant, and it will be equal to what? So potential due to shell in interior points, at all interior points, will be equal to gm, actually minus of gm over radius of the shell. Okay, got it? Yes, no? Okay, this is potential due to shell. Okay, and there will be some potential due to this mass. How much will be that? So potential due to this mass will be equal to, okay, potential due to the mass m, which is at center. It is minus of gm divided by a by 2, or it is minus of gm, okay, 2 gm divided by a. So this is minus 2 gm upon a, and potential due to shell is minus gm upon a. So it is minus of 3 gm upon a, right? But they are not considering the positive or negative sign. So it will be 3 gm divided by a. This is the answer. Is it clear? Okay, good. All right. Let us see next question. This is similar question once again. A body of mass m is placed on Earth's surface, which is taken from Earth's surface to a height h equals to 3r. The change in gravitational potential energy is. So how much will be change in gravitational potential energy? So let's call it delta U, or work done we can say. It is equal to potential energy at final point gmm divided by r plus h, and h is equal to 3r, minus potential energy at surface of Earth. Okay, this question is repeated many times, just values are changed, right? So it is equal to what? Minus of gmm upon 4r plus gmm divided by r. So it is 1/4, sorry, 3/4 of gmm upon r, or we can say it is 3/4 of mgr, right? Option C. Okay, good. You're doing this calculation very fast. Okay. Then let us see next question. A black hole is an object whose gravitational field is so strong that even light cannot escape from it. To what approximate radius would the Earth, okay, have to be compressed to be a black hole. All right. So if Earth becomes black hole, that means escape velocity is equal to what? Velocity of light, right? That is equal to square root of 2 gm divided by r. Okay. So here v will be equal to c. Okay, velocity of light. So light will not escape from Earth's surface. Okay. All right. So then what do we get? So we have to substitute these values. Oh, all these values and solve it. Okay. So it is 3 multiplied by 10 raised to 8, and we'll take square of that is equal to 2 times this is 6.67 multiplied by 10 raised to minus 11. Okay, the value of g multiplied by this is 6 multiplied by 10 raised to 24 divided by r. Okay, they are asking us about r only. So it is therefore r is equal to will be 2 multiplied by 6.67 multiplied by 6 multiplied by 10 raised to 33. Okay, 24 minus 11, 33 divided by 9 multiplied by 10 raised to, this is 10 raised to how much? 8 square, 16. Okay. Am I doing some mistake? 13, sorry. 13. Okay, 10 raised to 10 raised to 13. Right. Sorry. So then this is of the order of 10 raised to 17. You take it to numerator, it will become 10 raised to minus 17. Okay, 10 raised to minus 17 plus 13. It's 10 raised to minus 4, and 6 times 2 is 12. Okay, so this thing is of the order of 10 raised to 1, and 12 is of the order of 10 raised to 1. So we can, okay, yeah, so it will be of the order of 10 raised to 2, right? So 10 raised to 2 multiplied by 10 raised to minus 4. So answer will be 10 raised to minus 2 meters. Okay.